You can go ahead and pass them up then. There is, of course, a lot of bonus on this one, right? If you pay attention, there's like 10 extra points here to earn. Not that I think you guys are probably gonna earn them because there's probably not enough time, but oh, come on, really? Yes. I have not. I'll have to call you back, okay? Bye. Is the crazy Paul asking me if I've seen The Mandalorian yet? Of course, yes.
Was it actually him?
Yep.
Oh my
it was.
No.
Hey, Crazy Paul. Crazy Paul came to class after all, right? Yeah, there you go. So, do I have everybody?
What if we
Okay.
don't turn it in?
No, I need you to turn it in.
No, I did.
Okay.
I was curious.
Well, if you don't turn the quiz in, then I would be sad.
I might get a better grade on this one.
I don't know about that. Okay, so there are several purposes of the quiz. One is to introduce you to a curve that I have not really told you about yet, but it should be discussed at least a little bit, and it's this thing. Here I have t plus cosine t, comma 1 plus sine t. Let me try to explain what that is. Yeah?
There's actually two solutions to that curve. It just depends on where the wheel's orientation starts.
Where the what?
The wheel's orientation starts.
But I put the point at the origin.
No, where on the rim the paintbrush wheel starts. So if the origin is here,
Yeah.
the wheel starts here, then the wheel can start here. So you end up with the paintbrush going down first and then going up.
Mm-hmm. Oh, okay,
First
cool.
and then going down.
You're probably right, but I mean, I was trying to make the solution unique as to be kind to the grader, but I may have failed. But it's good that you realize I'm talking about the wagon problem. So, so what we're looking at is, I think of this in two things. Like there's t comma 1. So what, if you just had the position as t1, what would that be? Think about this for a second here. You have a path, r of t, t comma 1. What's that do? It's very boring. I can parameterize this. This is a parameterized path. It starts out at 0, 1, right? And it does what? It just goes that way, right? So this is t equals to 0 here, you know, over here somewhere, t equals to 1, whatever. And the motion's this way, yeah? So if I superimpose on top of that a circle, right? Let it trace out a circle as it's going. That gives you this kind of, well, I'm not done with it yet, but so if I add on top of this, you know, let's say, you know, well, let me just make it simple, you know, cosine t, sine t, then what that's doing, right, is it's sort of circling. If I add this to that, then I have a circle that kind of moves around it as I go. Let me just plot it over here. So like here it is. Let me move this a bit. And so of course this silly animator, if you don't fix it, it goes both ways, which we don't want. So there we go. This is called a cycloid. Let me try to superimpose a circle that it's going on. So let's see, what's the circle? The circle it's going is x minus t squared, I think. That's where it is. And then plus, it's always the same y, right? Y minus 1 squared equal to 1. Oh, thank you. There we go. So if you, I guess it would be better still if I could animate the, well, I mean, you can see the point, I guess, on the wheel if you use your imagination a bit. Let me slow my roll a bit here. So you can actually track, kind of see the point. Ah, well, I tried. Where'd it go? Oh, I guess we're out of. There you go. Now you can see it a little bit better. So if we, I mean, obviously I haven't set it up as my. I was trying to give my problem an annoying. You have to start it in a certain place, which just makes it obnoxious, right? But if you don't have to worry about all that, you can just add a circle to a line moving like that, and so you can imagine tracking the paintbrush like I was talking about. This is called a cycloid. So, yep.
Are you supposed to use the same V both like inside and outside the cosine, or do you like?
Nah.
switch the angular velocity?
Yeah, there's in your actual problem there's more, because you'd want to use V over R, which I gave neither of, so it's more obnoxious still, which is why it was worth 50 decipoints, as it's annoying. Let's see here. Yeah, if I do something like, oh, I don't know, 2. Well, that's wacky. So yeah, let's see here. I think that would have been appropriate because I had V and R both being 1. So like you want V over R for your angular velocity for this. To roll without slipping, V is equal to omega R. So if omega R are both 1, then the coefficient of sine and cosine being 1, it tracks. Now I have the angular speed is 2, which doesn't quite track with the V and the R, which, I mean, I should have omega equals 1 to get a cycloid, is my point. So I'm not entirely sure that the answer to that problem in the quiz I just gave is a cycloid. It might be something that's like a cycloid, but not quite a cycloid or something. But anyway. But but the larger point I wanted to expose you to here is the idea that you could think about taking 2 curves and sort of composing them in this additive sense, right? You take one curve and then add another one to it, and if you do that, you can create much more interesting pictures without too much effort, right? You can the world of your hypothetical curve examples becomes much larger with this idea. This is essentially the idea of epicycles also. Like epicycles are circles over circles. Yeah.
How do you know that the first curve is T1?
Oh, that's just a creative leap. But for this one, this is not the solution to the quiz, but mind you, this is like the quiz, but it's not the quiz. So this gives me velocity 1, 0, which just means I'm moving to the right with constant velocity. And I just put the 1 here because I wanted to make the circle up above the axis when we looked at it. It's just that. So, but the other thing, anybody get the last problem? What'd you get?
You got 2.
You got 2, you got 1, you got what? I got a 4. How'd you guys do it?
Turn the secant squared and then for tangent.
You used the hint? The hurt?
Yeah, it's a hurt,
The hurt,
bro.
yeah.
That was not a typo. Let me explain to you why. It was a hurt.
Was it?
So this is actually from my Calc 3 notes, so you'll have to disregard the first thing. This is not a Calc 3 problem, though. Here's the difference in Calc 3, just to give you a preview to Calc 3 just momentarily here. Nothing too big. In Calculus 3, we talk about how to do iterated integrals, like double integrals. And in there, we have a notion of integrating the integral. And so like, you do this one first, and then you do the outer one. So after you do the first integral over R, you get to here. That's exactly where you guys started. Although there's no 2 in this problem, because this one's a little bit different. This one actually is x plus y equals to 1, whereas you had x plus y equals to 2. And so this problem's slightly different, but the calculus is the same. So yeah, if you do this, you get a cosecant squared, which then integrates to cotangent, and you evaluate. This one gets a half. The one in the quiz did get a 2. And the reason for that is just that it's literally x plus y equals to 2. I'm asking you to find the area of a triangle with base 2 and height 2. So the answer is 1/2 base times height, which is 2. As I said, it was not a typo. That was a hurt, not a hint, because I'm trying to lead you down the garden path to make you do the wrong thing. Whereas the right thing to do here is just to recognize, oh, it's a triangle. All right. So let me show you the same problem my brother always puts in his Calculus 1 class. In the first test on integration, my brother invariably asks them to calculate this integral. Mind you, this is Calculus 1. So, like, how do you do that integral? Now, it's actually more of a kind of a unfriendly problem for you guys than for Calculus 1, because Calculus 1 doesn't even have the tools to deal with this problem. You guys can calculate this thing directly. Trig sub, right. But that's really not the right way to do this, in a sense, because what you're looking at is y equals the square root of 1 minus x squared, right? Which is also known as x squared plus y squared equals to 1. So it's a unit circle. You're just being asked to calculate the area of this sector, right? So the answer is pi over 4, because it's 1/4 of the area of a circle of radius 1. Yes, you can do trig substitution, but do you need to? Yeah.
Can that be on the final?
Can that be on the final?
Pretty please. Sprinkles and ponies and Mandalorian references.
With sprinkles and ponies and Mandalorian references. How do you put those things together? I don't know. This is not helping. This is not help. So you claim to not be a brony. This is not helping you. Yes, sir.
Can you like do that for any?
You put sprinkles and ponies together with a Mandalorian reference. What are these if not the words of a brony? Let's hear.
It's a guy who likes my logo.
Oh. Sure.
Sorry, I was referencing a previous inappropriate comment. Yes.
Can you do that with like any
Oh, any?
people that you're going to use?
Oh no, of course not. No. See, because all you have to do is something like, I don't know, this, right? And then my brother's, trick no longer is relevant, right? It's not some nice fraction of something you already know.
You could do that previously geometrically as a sector.
I don't think so. I think this is unpleasant.
So you just do that arc as a sector of the first.
But it's not that though. You see, because like, I mean, if it was this, sure, but it's not. There's this. I guess. Oh, you're saying, okay, fine. I guess I'll buy it. So you could do that sector and then add the area of this triangle, whatever it is. Okay, yeah, sure, yeah. You're not wrong. All right, let me put this away. The purpose of this example, my Calc 3 notes, these are my old handwritten Calc 3 notes, is simply this, is that for this problem, polar coordinates is the wrong choice. This is not a polar problem. Truthfully speaking, we should solve this with Cartesian variables, because it's just more naturally that. Anyway, oh, what's that other thing we do? You know, that thing. Oh man, time flies when you're having fun. Do you guys have any questions about the homework and time that remains here? All of them? Yes, sir.
The problems where it's like asking for the length of the curve and you have to do the arc length. I don't know if I was doing it right or wrong, but I was getting like integrals that I was like, there's no way I'm going to solve this within half a day.
Well, I don't know. Which problem are we talking about? If it's from the book, you probably could solve it.
That's what I was thinking. I was like, I'm
Usually there's like you gotta stick with it and look for the square. There's usually some kind of quadratic that appears. Which one are we talking about specifically?
It was 149,
Mm-hmm.
and x was dt, e to t minus t, and y was 4t, no, 4e, 2 divided by 2.
E to the t over 2?
Yes, sir.
Yeah, that one works out nice. Somebody asked me about this the other day.
You guys do like a surface substitution? Or?
Not particularly. The thing in, I just said, there we go. So the x derivative is e to the t minus 1. The y derivative is 2 e to the t over 2, right? So when you square the derivatives and add them, you get which gives us right. So e to the t over 2 squared is e to the t. But what then are you looking at here? Well, you've got a minus 2, a plus 4. That's a plus 2, right? So that gives you e to the 2t plus 2 e to the t plus 1, which you can write as e to the t squared plus 2 e to the t plus 1. Which is e to the t plus 1 quantity squared. So when you feed that to the square root, you just have to integrate e to the t plus 1. So yeah, that one's not bad. You just have to stick with the algebra there. So just expect that to happen with any of the book problems. Something like that will happen.
So I was confused because I was like, I wonder if I used like the wrong formula or something, because it looked hard at first. Like, it looked impossible at first.
It does, yeah.
But
That's.
I also did x dot. I did that derivative wrong.
Every one of these books is like a psyop by by the book. They're trying to psych you out. They're all meant to intimidate you into giving up, but don't give up. They're actually something you can integrate. And again, it's going to be it's almost always going to be a square inside the square root, but
Yes, sir.
or sine squared plus cosine squared is 1, something like that. Other questions? All right.
You're gonna give it to him?
I used to have this guy in physics who talked during the test like a lot. He sat there. This is actually the guy who was a brony. Not kidding. It just so happens. These stories connect. But he would sit there and he would talk under his breath like. And then I had this like older student. He must have been like 35 or 40, and like just like a dad figure. I don't know why he was there, but he was there in my physics class. And after about like 3 minutes of this guy doing this, he just goes, "Stuart, shut up." And it was like, thanks, man. I can't do that, but thank you. It wasn't that. No, he said something more constructive and dad, like, "Could you please shut up?" Or, I mean, there was some new. Yeah.
Way back, I forget.
Yeah. I missed it. I judged from the laughing. That's just as well.
That's probably better. I'm good.
Oh no? Oh, okay. Ah. Anybody else have a question? I think for problem 5, by the way, there was no vertical tangent, because the place where you might have had a vertical tangent, and there's at t equal to 0, both of the derivatives are 0, so that's neither a vertical nor a horizontal tangent. It may be a cusp. I don't know. I have to investigate it further. But so this is the thing that you guys should check on in your homework when you're finding vertical tangent or horizontal tangent. You want one of the derivatives 0 for the parameterization, but not both. It's like a vertical tangent has dx dt equals to 0, but dy dt non-zero. A horizontal tangent has dy dt not changing, dy dt 0, but dx dt has to be non-zero. So these are the, at least that's how the book defined vertical and horizontal tangent. So, okay, let me go on here if I can find one. I did have more area integrals to do on my phone here if I can find them. Oh, come on. Let's see here. No, we did that one already. No, we did that one already. I'm going to get one eventually here. Well, that one was good. Here it is. So I'll draw the picture for us. Suppose you're looking at this circle and then that circle. This one has radius 1, and this one here is centered at 2. All right, and we'd like to find the area. We'd like to find the area of this region out here. So how would you calculate this area? Well, some things I already know, right? The polar equation for the little circle, that's pretty easy. That's r equals to 1, right? What's the polar equation for the larger circle? I don't know right off the top of my head either, but I do know how to write down the Cartesian equation for that circle. What would that be? What's the Cartesian equation for this circle? 2? If it's centered at 2, it's got to be radius 2. Right? So my point, I would point out to you that's x minus 2 quantity squared, right? Plus y squared equals to 4. I can see that because we're looking at circle center at 2, 0, radius 2. So this is the parameterization of such a thing, right? So then, let's see here. How do I find the polar equation? Well, let's work it out, right? So this is r cosine theta minus 2, square that thing, plus r sine theta, quantity squared, equals to 4. Multiply this out, we've got r squared cosine squared theta minus 4 r cosine theta plus 4 equals to, oops, sorry, my bad, plus r squared sine squared theta equals to 4. The 4's cancel. And, oh, look at that. It's a package deal. So that's r squared, right, minus 4r cosine theta equals to 0, which we could rewrite as r squared is equal to 4r cosine theta. I feel like I did something wrong here. No, never mind. I just remembered it wrong. I remembered that the book had a 2 cosine theta here, but it doesn't. It has, in fact, that 4 is there. So what's next? Divide by r, right? And you get what? R is equal to 4 cosine theta. And by the way, like, we're not losing any information, right? Because the r equals 0 is still there. We just choose theta equal to what? Minus pi over 2, right? So we're still going to get r equals 0 from that. Pi over 2, let's say. Anyway, so there you go. The equation of this circle right here, apparently, is r is equal to 4 cosine theta. So we worked that out. Now that was given in the book's problem, but I thought it would be constructive for us to work it out. All right? So we did. Now how do you find the area? So which is the inside, which is outside? And is that a reasonable question to ask here? I think that's a reasonable question, right? If I take any ray from the origin like this is the inside, that's the outside, right? And it's the same no matter where I am, right? Always the same in and out. See that? So this is my inside radius. This is my outside radius for the setup of the integral, and here we go. So the area is the integral. Oh, hold the phone. What angles should I integrate over? So I need to figure out this theta max, right? And down here, theta min. I feel like you could make music with that if you were, if you spent some time on it, you could develop it. What's that? That's what I listen to. No, there was a. All right, focus. So 1/2. Oh, I don't know what those are though. Can you figure those out for me?
1 cosine theta equal 1 cosine theta is 4. So 1/4 inverse cosine
So yeah, inverse cosine of a quarter for the upper one, right? And let's be lazy here because it's, I don't know, like you could figure out that this is minus inverse cosine of 1/4 as well, right? So we can, but why don't we just double it and do the integral from 0 to inverse cosine of 1/4, because that's, a little bit easier. 1/2, and then we do r out squared minus r in squared d theta. That was the formula for the integral. So the 2 and the half cancel. We have integral from 0 to inverse cosine of 1/4. My r out was 16 cosine squared theta, and then minus 1, yeah? Which is the integral from 0 to inverse cosine. I'm getting really tired of writing that. I should have called that something. I did. Why didn't I use theta max, dummy? Inverse cosine of 1/4. 16 cosine squared is actually 8 plus 8 cosine 2 theta, right? So 8 minus 1 gives me a 7, right? Because cosine squared is 1/2 of 1 plus cosine 2 theta. So 16 over 2 is 8, and then again the 8 minus 1 is 7. And we integrate this thing. We get 7 theta plus 4 sine of 2 theta. Evaluate this thing from 0 to theta max. Haha. I learned. Now this, okay, you could put it in your calculator, right? But it's kind of fun to do this. 2 sine 2 theta. Wait a minute, no. What is sine 2 theta? That's 2 sine theta cosine theta, is that right? Yeah, that's right. If I check it at pi over 4, that works. So this I could trade for, 7 times the inverse cosine. Oh, it's going to be ugly anyway. Why do I even bother? Plus 8 times the sine of the inverse cosine of 1/4 times the cosine of the inverse cosine of 1/4. See, all that jibber jabber earned me the right to simplify that to 1/4. I don't really think it was worth it. but there it is. So that's actually 7 inverse cosine of a quarter plus 8 over 4 is 2. 2 times the sine of the inverse cosine of a quarter. Now, if you think it would have been easier to just plug in inverse cosine of a quarter into my original formula, I think you'd be right. So we can try it out. 7 times inverse cosine of 1 divided by 4. So that's about 9.22 from the first term. Oh, 9.227 actually. And this guy over here, this guy gives me about 1.936. So if I add that to my, I get something like about 11.116-ish. Of course, the exact answer is right there, but there you go. Any questions? Yeah.
Can't you figure out the sine of the inverse cosine exactly?
Oh, yeah, that's true. But I just,
I mean, it's not necessary. I'm just kind of curious.
oh, yeah, we can. So if we, let's see here, I think we just need to make a triangle, right? So if I say theta is equal to inverse cosine of a quarter, then that makes cosine of theta equal to 1 over 4. So the triangle I'm looking at has got an adjacent side of 1, hypotenuse of 4, and that makes this the square root of 15. Here's your theta. So then sine of theta, which is what you're interested in, right? Because that's sine of inverse cosine of a quarter. Sine of theta then would be like square root of 15 over 4. So that's how you do that. The thing I'll get stuck on if I forget how to do this in a day is like this initial step. This seems like nothing. It seems like a non-step, but this is actually everything for this calculation. This recognition is everything. But anyway, sorry if this is bringing bad memories back from pre-calculus for you, but because we asked them to do all that kind of stuff in there, right? I mean, that's what I saw in the, I've graded the final exam from pre-calculus for like the, we offer it, I think LCA has a like AP pre-calculus class, and then we tend to grade those in the math department at the end of the semester. So it's important not to be in the math department at the end of the semester at the wrong time, because if you're there and then the chair, Professor Young, sees you, he'll be like, oh, hey, you want to help grade the pre-calculus final? And you feel like a real jerk if you don't. But on the other hand, you just signed up for like 2 hours of pre-calculus final grading, So it's a mixed bag. Yeah.
Weren't you excommunicated from the math department?
I am in exile right now.
What'd you do?
I left. Worked for the Navy for a year, and then I was in Alabama for 2. So I lost my office. Although I was before in the 3rd floor of engineering, which is, well, there's only 1 floor of engineering, right? But the 3rd floor where engineering is, where Dr. Joseph's office is, that was my office previously. I'd like to get that back, but oh well. Yeah.
What part of Alabama?
What part of Alabama? I lived in Tuscaloosa. I worked in Livingston. So. You're from Alabama? Where?
I'm like an hour and a half, 2 hours from Tuscaloosa.
Okay. Yeah, I don't miss the weather. You don't either? I don't know. I had a neighbor who grew up in Alabama, and she'd always be like, when it got to be 80 in the summer, she'd be like, oh, finally. It's like, what's wrong with you? Like, well, she just, that's how she, I mean, like, I don't know, there's mosquitoes in Alabama at Christmas time. Like, it's messed up. So, anyway, oh, I think I'm out of time. Oh, sorry, Taylor. So that quiz was